Okay. Hello everyone. My name is Taylor. Welcome to Intro to Rocketry. So the purpose of this presentation is going to be to outline the top level theory. I want to just kind of dissect the rocket a little bit for the new members that don't really know anything about the team. You find that when you initially join the team, there's a lot of complex language, a lot of niche terms for everything. At the end of the day, I do believe that from this presentation, even a guy that's been on the team for 3 years is going to learn something because I have been in a lot of conversations I had no business being a part of. Quick overview of what we're going to do. We're going to talk about what the team is, the competitions we compete in. Then that should help explain the purpose of a lot of the subsystems a little more. Then I'm going to do a little activity where we put everything together, and then I'm going to end it with advice for the new members. Quick overview of me. I joined 2021, Winnie 3.0. I am so old that people that founded the team were on the team the same time as me. I was pilled lead from 2022 to 2024. Alongside that, I was an airframe member. I helped become, I don't want to say a pseudo mechanical lead for Winnie 4.5, but I was oddly involved in the flight simulation side of things as well. That ultimately led to me being team lead last year for the launch of Winnie 5.0, the team's first fully nominal launch. I've been to both competitions we compete at once, and for uh, FCC 2022 and LCC 2025, I was watching the crap out of the streams and aware of everything that was going on. So I know quite a bit, probably not everything, but I'm going to try my best. Um, some clarifications for this presentation. Everything I know is based off of the state of the rocket today. Almost anything can change based on even the rules changing. Very notably, I'm pretty sure the payload ramble, some of the rambles are going to change literally within the next 2 weeks. I might ramble about what rules it sounds like we're going to change, but yeah, regardless, that's kind of my ranking. You'll see very quickly by the level of depth I can comfortably reach on some of these subsystems that I know a little bit more than others. So hopefully in the future, someone who knows more about the other subsystems can ramble better than me. I don't think this presentation is going to be the best presentation ever. I think there will be gaps in everyone's knowledge about the rocket from this. Um, I put in probably 20 hours into this slide, and well, the other thing I'm going to mention is I had to draw the line somewhere. I can't explain the entire rocket. I could probably spend 10 hours here rambling about just the bottom half of the tubing section and all the complex conversations we had about that and the development and the history. Um, so yeah, I had to draw the line somewhere. Quick overview of who we are. UMSATS. There is the satellite team and the rocket team. We are part of the same overarching executive team, but we don't really interact much when it comes to design work. I made this joke. We both really wish we could unite one day because the rocket team would love to launch high enough to put a satellite into orbit, and the satellite competitions have a hard time gaining the trust of an agency to put their product out there. Um, so one day, hopefully, we could merge efforts. Quick overview of how the structure of the team works. There are members, which a lot of the people starting off are. Then there's system leads who are in charge of most of the members. I'll ramble about what the subsystems are, though there's 1 to 2 leads for each of those subsystems. And then on top, there's an executive committee, entirely elected individuals to run various tasks. Quick overview of the execs. Um, they're responsible for the upper level things. Anything that's not a design typically falls into an executive position. The team leads, rocket lead, satellite lead, They are kind of the overall program managers. The business leads is in charge of promotional activities to a certain extent, as well as a lot of the money acquisition projects, fundraising, etc. HR is mainly in charge of member delegation, monitoring who's where, who's what, why, how regarding member acquisition. Finances is the person in charge of managing the funds we get, a job I'd never want to have. Promos is in charge of the websites, the social media, as well as helps business run some activities. Project manager, similar boat to promos in business, they're in charge of running some of these activities, the outreach events. Whenever we have a booth at the tech talk fairs, project manager is also involved in that. Document manager is in charge of managing the documents, creating documents, making the documentation life easier on everyone. Lastly, president is in charge of everything. System leads are appointed positions rather than elected positions. They are in charge of their individual subsystems on the team, as well as they are the face of the team. So if you have a question about a system, you'd want to go to the system lead first. They also, yeah, design everything. All in all, it's weird to say this, but UMSATS has 20 to 25 people in a leadership position. So if you ever want to be a leadership position, it's fairly easy to climb the ranks in that way. Now we can talk about what the heck the rocket is. So a quick overview, or yeah. So a Formula car, I think if you've been to their info session, they're gonna say we're not a car. We're more of a go-kart. We're a hobby car. Similar with SAE Aero, they're not flying humans. They're a big hobby plane. That's kind of what we are as rockets. We're not shooting rockets into space. We're not massive 20-foot diameter rockets. We're more of this hobby rocket um, team. The term sounding rocket is used a lot. Sounding rocket is a rocket that doesn't go to space, functionally speaking. Missiles also are sounding rockets. Unlike missiles, we land safely, hopefully, probably. We use non-propulsion lands. However, there is a sense that this does translate well to industry because we are working with carbon fiber that most industry is using. We are developing our own propulsion system, which we'll ramble about. Translates perfectly well to industry. You hear about propulsion teams in the coast, they go straight to SpaceX right after. And obviously, a rocket is a rocket is a rocket. The dynamics for all rockets from a rocket of this size pretending it's able to launch. And SpaceX, there is a lot of overlap throughout all sizes of rocket. I like to use this just to showcase where we are height wise. We fly right now in the 10 to 20,000 feet range. Planes go around 30 to 35,000. So we're not even at commercial plane height at the moment, but it's still really high to the point that even in clear skies, you're not going to see it. Student world record, I think, is 100,000 feet. Space shot, or whatever that means. Gravity still applies to it. Where the heck do we launch? We launch at these two competitions. The first is the International Engineering Rocket Competition. I got the term wrong. It's an international competition. Whoa, it's in the name. 170-ish teams from 26 countries was the last year's statistic. It's huge. It is a massive competition. Name a university they've attended it. Name a university we might have beaten them to technically. Um, it takes place in Midland, Texas. It used to take place in New Mexico with the name Spaceport America Cup. Ultimately, that organization of people decided they wanted to do more, and so they found a different launch site so they could do more. The other one is the Launch Canada Challenge. You'll hear about that. It gets the name LCC all the time. It's the local one, the local talents. There's a couple high school teams, but name a Canadian university, and they're either going there or hoping to go there, as long as they have engineering programs. It takes place in northern Ontario, Timmins, 5, 6 hours north of Toronto, 20 hours from here. They're both far from here, but you'll see why they're far from here. Quick overview of what the heck they're going to do in the competition. So, the first couple days is the check what everyone else is doing out, calm before the storm kind of days. You get to go inspect everyone's rockets, ask them a million questions, take pictures of this. I like this idea, I like that idea. While that's happening, the judges will come around. They'll typically give you a heads up, but they'll look at your rocket and they'll say, "Nose cone, what's that made out of? What analysis have you done for it? Body, talk about this, talk about that, talk about that." Then you will get some competition scoring based off that, based off what they see of the construction of the rocket and your ability to present it to them. There's also info sessions in rooms over typically. At Launch Canada, it's typically huge. At IREC, it's rooms like the one we're in, E2351, where it's whoever can fit in the room gets to listen to whatever industry's talking. Um, the another thing they typically do is pre-flight inspections. They do a rocket inspection there, but the purpose of these pre-flight inspections is to spot anything that you might want to take a couple of days to address. They'll either say, "Yeah, I'm cool with that rocket flying." "Yes, I'm cool with that rocket flying if you fix these components together, if you tape this, if you screw in a bolt here," or they'll cut you off there. Um, Lastly, team focus. After the first 2 days that I call the calm before the storm, even then you're probably going to be staying up till 1 or 2 in the morning working on the rocket. Um, then you typically get 4 to 5 days to launch. Um, and the first thing you're going to want to do, obviously, once you get there, is assemble the rocket. When you hear the word ConOps, I use the word ConOps again. I use the word, sorry, not again, a lot. I use the word ConOps a lot. Basically, ConOps is the moment you wake up the day you plan on launching to the moment the rocket lands is ConOps, concept of operations. What are you doing before you launch the rocket? What are you doing after the rocket lands? What is happening to the rocket during the launch? This is when ConOps begins as you start to assemble the rocket, or when you wake up the day of assemble the rocket. Once you successfully assemble the rocket, you're going to line up for this last inspection. They're going to be pretty harsh on you because they're shining the rocket and they're saying, "Yeah, I'm cool with this thing going Mach 1. You nuts? This thing's going to easily survive." Um, Another thing that really makes it fun but also stressful and intense is the fact that pretty well at both competitions, there's a first come, first serve. If you are there at 6 a.m. and your rocket is ready at 8 a.m. and no one else's rocket is ready at 8 a.m., you get to be the first one to launch on that day. And so, yes, I'll also mention there are incentives for launching earlier in the week. They don't want everyone to ensure their rocket is pitful, patful, because I think I'll ramble about this later. You might not get to launch the last day, as well as no one wants to launch all 40 rockets that are trying to fly on the very last day and not any in the previous 3 days. So this first come, first serve initiative, as well as the bonus points, definitely adds a bit of stress to it. Let's say your rocket passes. Not always the case. Then you take your rocket to the launch pad. As you can see, there is a launch rail here. This guides the rocket, so then it needs a little bit of momentum to fly stably. I'll ramble about that later. Now is also the time where if you have electronics, you're going to want to turn them on. A lot of the electronics have a battery life of 4 to 6 hours. They're designed to be easily accessible from the outside somehow. I'll ramble about what switch mechanisms there are later, but now would be the time you turn on the electronics, take your photos. Yeah, this I think I was planning on rambling about the launch rail. This is what the setup looks like. There are rail guides attached to the rocket that attach to the launch rails. We can make our own. We typically use theirs. This is going to be angled at around a couple degrees, under 5 degrees, because they don't want it coming towards you, believe it or not. They want to have some ability to get it away from you. As well as, I think that's all I wanted to ramble about. Then you go away from your rocket. You make sure you have proper connection. There's GPS modules on the rocket so you can find it after you launch. You're around a kilometer away when it's happening. Someone else gets the right to press the button. Sadly, you can't. But you basically say, yes, we have connections. Yes, there's no other concerns we have about the rocket. Fly that thing. Then your rocket flies perfectly. Now, have fun finding it. You have GPS modules. You typically do have a good idea of where it comes from, where it flew to based on the GPS modules. But because they don't want to launch the rockets downtown, believe it or not, you're in the middle of nowhere. Nature's everywhere. At IREC, it's sand everywhere. There could be scorpions buried somewhere. Um, and it's hot out. At LCC, you're gonna find that there's dance forests, and water could be anywhere. The other thing is, depending on when you launch, some days you have to launch one day and retrieve the next, or, which we've had as well, retrieve one day, fail to retrieve, then have to go all the way back. Sometimes it's a 2 hour drive from the nearest reliable Airbnb to try to get that rocket again. Um, I mentioned this before. The launch window in a given competition can be very slim, so it's very important that we're ready the instant we can be, and that we stay ready once we are ready. If there's cloud coverage, they won't launch the rocket into the cloud. If the winds are pretty fast, the line is 30 kilometers an hour or higher, they will not launch. Rain, they won't launch. Sub-zero weather, I believe they won't launch. I'm gonna also mention that whatever the payload's gonna be, you're gonna want to embed that into ConOps somewhere somehow. Back to the competition discussion. IREC typically has, because they want to launch 170 rockets in 4 days, they're not going to look at your rocket nearly as strictly as Launch Canada will once it's there. But until they're there, they have very, very strict rules that if your rocket isn't following, good luck being allowed to launch. Um, Regarding competition categories, they have 10K, 30K, SRAD Solid, SRAD Hybrid, um, SRAD Liquid, 45K Double Sage, 45K SRAD Double Sage. They have like 8 to 10 categories. And I mentioned this before. The rules are strict. You follow them, you get to launch. No questions asked. LCC is the opposite. LCC, with their rules, they're going to say, do what you want, but we're going to stare at it with a microscope. And if we don't like an ounce of what's there, you're not launching. Um, you don't have to go to a certain height. You can pick a height. Rather, they just have beginner and advanced. If your motor is off the shelf, advanced. Um, if your motor is if your motor is soon researched and developed, advanced. If your motor is off the shelf, basic. If your motor is a certain strength threshold, advanced. And yeah, both of these have largely the same scoring schematic. Um, they have a scoring system of, firstly, the Bearman score. Bearman score is based off of how close you are to what you predicted you would fly. If you tell either competition, we're going to fly 10,189 feet, and your rocket goes 10,189 feet and then goes right back down, then you get a lot more points. You get a lot of point potential. Professionalism, as I discussed before, if you're launching first, if you're timeliness, you get some points there. Report quality, analysis, structure, design. Did you actually look at your entire rocket and think through everything? You get good points there. They want to see good engineering principles. They don't want to see or have this on a rocket because we want to take a risk. Um, Lastly, a nominal flight gets you a lot of points. I'm going to classify a nominal flight as firstly, you define everything your rocket's going to do. It's going to deploy a drogue, then it's going to deploy a main, and then the payload's going to do the hokey pokey, and then it's going to land. As well as there's no notable damage on the rocket. It's partially classified to be that if you can put your rocket together and insert a new motor and launch it again, then you get those points. If there's a major damage that would take a day or two to repair, then you don't get those extra points as well. I did an interesting scoring analysis. You'll find that they're largely the same. Behrman's score for IREC, green is Behrman's score here. Yellow's Behrman's score here. For Launch Canada, it has way less weight than it does for IREC. However, it still is largely the same scoring schematic where it's about 50-50 analysis performance. Technical application is the only thing that LCC really showcases, which is fairly hard to quantify to the point that I forgot how they quantified it. Um, but yeah, I'm going to mention this here as well. You can find information for both websites fairly reliably and easily. Now that this is here, I don't expect, or sorry, yeah, let's go quickly to this IREC. If you go to documents and forms, there are two documents I mentioned here, rules and requirements, design test and evaluation guide. As you're designing, I think it would be a very, very good idea to go over these documents. They changed the UI on me. Okay, let's say I wanted to look at painting the rocket, because I think everyone can understand what paint is. I'll quickly skim through the rules and requirements. Let's see. Event logos and style guidelines. How about that? Oh no, that doesn't really show me anything. I'm doing this live, by the way. There was something here. They changed it on me. Those sons of guns. Okay. Uh, the other document you'll want to look in is called the DTAG, Design Test and Evaluation Guide. Identifying markings, 8.7, right? Does this tell me anything that I should know before I start painting the rocket? Maybe it does, maybe it doesn't. That's 30. All rockets should be labeled with team name number, GPS tracking frequency. Okay, maybe let's involve that in my painting, right? Team ID number. Let's involve that in my painting. And so a lot of the questions I typically get asked, hey, do you think this would fly? I literally just go here first. Similar ordeal with the Launch Canada website. You just go to LCC or launchcanada.org, and for the IREC one, you go to ezrarocket.org. And now you can find very quickly, you see teams, rules and requirements, design test and evaluation guide. So whatever question I have, I would look here first because these are the rules that even I'm gonna have to follow, right? So yeah. The other thing I'll mention here, if you go to Ezra Rocketry on YouTube, these guys are really good for showing every launch ever. And you can see they even put all of the launches here. So you can just, I want to watch Chosin's launch. It's an ad. Screw ads. Similar ordeal with Launch Canada. The only thing is they don't do the timestamp thing that iRank does. So you're gonna have a hard time finding them, sadly. I can remember where our launch was, but beyond that, I can't remember anything else. So yeah. Onto payload. I should have segregated each section. Now we're talking about subsystems now. The first payload, system I want to talk about is payload. Payload is the mission of the rocket. You believe it or not, don't often launch a rocket for the sake of launching a rocket. Every rocket has a purpose. Whether that be deploying a satellite, whether that be the James Webb Telescope. It's a rocket that brings the satellite into orbit, not the satellite that is just taken along because we're going to launch this thing anyways. The payload, in other words, is the purpose of the rocket that we fly. In our context, it is a small experiment that utilizes the rocket's flight. I call it backwards because I just said that every rocket needs a payload, but in our case, we are launching the rocket first, and we're thinking, hey, we're going to have a rocket that's doing this. What can we learn from it? Um, However, this experiment still has value. If the payload is designed right, it can utilize the rocket's flight well. It is the tester experiment that is being conducted as we are launching that doesn't interfere with the rest of the launch at all. This is a rule I've heard of rumor that it might change. However, in our context, we have to design a payload to be this kind of cuboid structure. It's called 3U. 1U is a 10 by 10 by 10 centimeter cube. You stack three on top of each other, you get this 3U monstrosity. It is,
If you don't mind,
yeah,
just wondering, what did Minnesota use that payload? I know it's their experiment.
I forget what this payload exactly was. I will say there are other competition reports in the Google Drive. Um, I could, I should put, I'll mention how to find those other reports in the drive to find it. I'll ramble about some of our other payloads as well later. That was a good question, good catch. Um, Another thing I'll ramble about here is that we have these maximum size constraints, but it has to be at least 2 kilograms. So you have maximum size, minimum weight, and then it has to do something useful in the rocket, which is annoying because it's really hard to make contraptions like this at least 2 kilograms. It used to be at least 4 kilograms, which is even crazier. You'd see teams that are like half metal just to meet that weight. The other thing I'll mention about IREC is because they're trying to launch 170 rockets, if you have a payload that is detached from it, that's two things to recover. And so if they have 170 things launching and everything splitting into two, that's 340 things for them to factor in recovering. That's a lot for 4 days. However, you'll see that Launch Canada has none of these restrictions. Payload scoring is very subjective, which I don't like. Um, you get 400 points for the objective, 250 for the overall construction, 50 points for how well it blends within the ConOps, how well it functions within the ConOps, and then 300 points depending on how it works, if it actually works as planned. They have the rule that if your rocket goes kaboom, you get 150 points because then in theory you don't actually know what would have happened. Quick overview of some of our previous payload projects. From 2018 to 2022, um, the idea was we wanted to simulate a rover deployment after launch. However, I get the overall idea was it would be attached to the parachute system that would fall out, and then the rover gets to simulate being deployed. I, as field lead, decided to obsolete it, and that was feedback from a judge told me this. I couldn't really help myself but agree. You don't use the rocket at all when you have a payload that goes up, down, and then deploys. You could test that entire mechanism without the rocket. You could just put it over there, go a kilometer away. Doesn't work. Next is this didn't actually have a name. The idea was we wanted to get a payload going out pretty quickly. We wanted to analyze the properties of a non-Newtonian fluid throughout launch. We wanted to see what the heck would happen. Um, there is GoPro footage of it somewhere. Uh, I forget what the in-depth results of everything was. We were initially going to plant a plant with this fertilizer after launch as well, but the overall idea was just to learn as many lessons as we could. Um, Fun fact, this was the first and only nominal payload and first and only successful flight we've had on rocket so far, which is funny because it was a rush payload and many valuable lessons were learned from this payload, however. The recent couple years, we had a project called Pulse. This was unsuccessful because it was definitely us chewing way more food than we could swallow. The idea was we wanted to mimic. Oh, you can see it. I've lost it. Wait. We wanted to mimic the brachial artery veins, some version of it throughout the flight. However, we did find throughout the entire process that we couldn't find a true advisor. So then we said, cool, let's make it a concept. However, there was other project management issues regarding everyone that was a member when it was initially on the team wasn't a member the year after, and so there was knowledge transfer concerns. Um, that being said, it was a really cool idea, and it was a great way to cement the scientific identity we have. However, one of the major lessons learned, which is why I call the payload the hardest team, is that they have such an obscure problem where you have to do something someone's not done before, do it well, and have it fit in this niche minimum mass cube. Um, However, the payload still has a lot of purpose to the team. First thing I'm gonna mention is that if you don't care about the rocket, that pulse idea was really cool. If you're a civil engineer and you hate rockets, well, our rocket is going to analyze fake blood vessels, and it's going to be a concept that we could analyze during flight. The other thing is that all the teams have incentives, all the competitions do have incentives for payload. It does feel like the vestigial organ of the rocket. However, there is a lot of good value for having a payload on the rocket. Next, I'm going to ramble about the propulsion system. These are kind of brand new slides to me, but I'll start off by rambling about the current system. The current system is a commercial off-the-shelf system that motor classes are determined by letter, the number, based on impulse. Impulse is the integral of a force. Basically, the more force you emit over a time, the higher the impulse. We currently are in the upper and lower end category. We've launched with an N1800 and an M3400 motor class at the time. I can now ramble back to LCC standards. An advanced launch is an O category motor or greater. Quick overview of how fuel works. Or, yeah, there's three categories that I rambled about before: solid, liquid, hybrid. It is literally as is said. Solid fuel is a solid material. The entire reaction is through solid, such as aluminum perchlorate, burning and emitting a fume and pushing the rocket up. Liquid is entirely a liquid fuel. Hydrogen, kerosene, methane, etc. I've seen a lot of people do biofuel with liquid methane, which is kind of interesting. Like they turn cow dung into rocket propellant. Lastly, there's a hybrid fuel, which uses a liquid of some sort to emit an oxygen reaction for the solid. That brings us to. Never mind. Haha. Going back to the current system, we have two commercial off the shelf distributors, Cesaroni and Aerotech. You'll hear the word Cesaroni a lot more in Launch Canada, or a lot more with us because Launch Canada directly deals with them and they are Canadian. The caveat is that they have slow lead times. Aerotech has better lead times. They are American, so it's easier to get it in America. Quick overview of the motor casing. The motor system. There is a refill, which has these codes M3400 and 1800, and these motor reloads go into these motor cases. The motor case consists of a closure set and the overall casing set. Sorry. The reloads are one-time use, but if you don't damage the case, you can use them a couple times. When we aim for the motor, we look at things such as thrust, burn time, impulse, etc. I'll ramble about some of those parameters and why they matter later on. However, it is a bit of a bottleneck because we are limited to what is available in a market and not what is available in-house. And we don't really have the ability to modify parameters. We just have to buy what's there and live with whatever garbage lead time or price they give us. This is what it looks like. The motor casing is there. That's the motor reload. There's an igniter, which you put at the bottom below here. And yeah. Now I can ramble about the hybrid propulsion system. We use a combination of NOS and ABS plastic. So we use laughing gas and Lego blocks, and we merge it, and that's how we are currently developing our own propulsion system. Fun to think about. We call it Project Sunfire. It started in 2022. As of now, we hope to have a stationary motor test, a static fire, by 2026, and then look to have it in 2027 in a flight. This is what we call the small scale hybrid test. We wanted to verify initial calculations and not spend the entire house on a system. So it is the motor's about this long, but it did verify a lot of the analysis we had already conducted. Quick system breakdown of where they're at so far and how they delegate their own tasks internally in this hybrid program. Um, they use an ABS plastic cylindrical bore for the fuel. As we discussed before, there's an oxidizer that is going to go in there and make this ABS plastic way more reactive. ABS plastic is basically hydrogen chain. I think it's hydrogen. It's basically a very combustive chain. This is an ABS, but it's in the form of plastic. So we can 3D print our fuel, which is really cool. Then there's a nozzle, which has the objective of accelerating whatever combustion reaction, which does create the thrust and impulse we want. Then they want to have the fluid flow in a specific orientation. That's when the fluid supply system comes in. They want to inject it in a certain orientation and at a certain rate, as well as they have the interesting issue where liquid NOx is not fun to transport, and so they want to have a filling station that they can quickly go up to the rocket and implement that fuel. So then we don't have to sit with fluid that doesn't want to be liquid. Lastly, it's not lastly, is it? Okay. There's an igniter system which is in charge of burning the motor at a certain rate and orientation and for a certain duration of time. They want the motor to burn for as long as possible to ensure that everything is reacted and we don't lose a lot of potential height. And then there is an electrical system. And then, yeah. There's also an electrical system which is in charge of all of the electrical components, which involve the valves, load cells, as well as what is going to cause the uh, igniter to ignite from far away, because we obviously don't want to be 2 feet from it. We want to be a kilometer away from it. There's also a test op subdivision, subsystem, which is in charge of what fixates the propulsion system for testing. This is a good example. As discussed before, it started in 2022. Over 50 students to my account. It peaked at around 24 members have worked on it. Santa Clara was 2026, and they want to implement it into the rocket 2027. Um, just came in and locked the door. Okay, whatever. Next up, the breaks after this, I promise. Flight dynamics. This was a brand new subsystem that I invented. The idea is the purpose of this team is design the fins, the nose cone, to optimize the Behrman score I discussed before for flight simulations. They're also in charge of specing the commercial off-the-shelf motor, and hopefully, as years go on, more and more and more thorough aerodynamic analysis. In case you didn't know, the top of the rocket is called the nose cone. The fins on the rocket are called fins. For simulations, we currently use a software called OpenRocket. There are other alternatives for OpenRocket, Rosarrow and RocketPie being the two most discussed. The idea is we trust these guys who are, I believe OpenRocket was a master's thesis project. Um, they we put it all in this software and it spits out flight projection, speed projection, stability, etc., etc., etc. Everything we care about for flight simulation. The overall idea is that the CAD model, the physical models, and OpenRocket should all, to some extent, agree. Um, it uses the sizes of everything, the masses of everything, as well as you can input commercial off-the-shelf motors, or you can upload your own thrust curve, as well as wind speed. You can implement whatever wind speed will be there, and it factors that into the calculation. Oh, what? Okay. With all that being said, does anyone have any ideas of reasons OpenRocket isn't going to tell us an accurate apogee? That's one. What could we get wrong? Off the top of my head, beautiful. We could get the mass wrong. We could get any of these dimensions wrong. We implement coefficient of drag. We're probably going to get that wrong. The motor selection is going to vary. Um, Pretty well everything we input could be wrong. to some extent. And as we discussed before, we want those points for accurate altitude, right? And so there is kind of some risk we do impose at the moment for trusting everything for open rocket. As we discussed before, our good guess for open rocket is the best we have for a lot of the points we could be getting. We rely on open rocket for a podium position, which is crazy to think about. Oh, there we go. That's where this project comes in. A subdivision of airframe right now is the air brakes project. The purpose of air brakes is to allow us to be more accurate with our altitude analysis. The idea is we aim for an 11,000 foot flight, then we can employ these brakes called air brakes that induce a ton more drag. So then we could slow the rocket's projection down to 10,000 feet. And then we can sell it. This allows us to account for all of this potential information being wrong, as well as it's a cool project. It started a little over a year ago. We're hoping to implement some variation of it now, or sorry, in this upcoming rocket. Um, but there's a lot of math and science to it, and the idea of the system is that the first system's going to suck, the next one's going to be a little better, next one's going to be a little better, next one's going to be a little better, and as those years goes on, we get a better and better Fairman score. Back to flight simulation discussion. Some of the values that you'll see matter. The first one is the stability margin. The purpose of the fins is to lower the center of pressure and keep the center of gravity above. I believe the metric is calibers, aka the however many times the diameter of your rocket, a caliper is the diameter of your rocket, is above between the CP and the CG. So stability factor of 2 means that you're 2 calibers above your center of pressure, your center of gravity is. Why does rocket stability matter? Well, as we discussed before, there's these launch rails that are only 17 feet tall. And so you have about 17 feet to gain enough momentum to safely fly this rocket, basically. That being said, there is such thing as a stability that is too high. Everyone has a different upper number. Between 4 and 6 are the numbers I've heard the most. The idea is if you're at a certain stability, your rocket starts to go with the wind instead of go on its projected path. So we have to do some level of analysis through Open Rocket or rather or etc. to ensure that we are stably flying. It's pretty well worded in the requirements. Next thing, as we discussed, velocity off rail. You have about 17 feet to get to a certain velocity. The number that is safe is 30 meters per second. However, requirements are going to say 15. If you're in the 15 to 30, you typically have a discussion with the judges. They're going to say if your wind speed is less than 15 kilometers an hour, we're going to trust this flight. That being said, it's also outlined in the requirements. It is a value we're going to watch. We want to make sure that we are adequately fast off the rail. Top speed. If you're at Mach 1 flat, then the drag is really, really high. And so you want to avoid Mach 1. You want to punch straight through it or not hit it to begin with. Supersonic flights generate a lot of heat. Subsonic flights do allow us to get a lot away with a lot. Historically speaking, we've had Mach point 0.8 to point 0.9 flights, which is really fast still. But that has definitely permitted us to do a lot dumber stuff than this year's flight. Apogee, as we discussed, Berman score. The other thing is if you're not in certain thresholds to begin with, you won't get any points at all, which is really unfortunate too. For Launch Canada, we put in a number that was 2,000 feet less than we accidentally hit. Oops. We didn't get any points. Arguably could have been the difference between a podium and a not podium spot for us. Quick overview of the nose cone design. For subsonic flights, a round tip. For a supersonic flight, a really pointy contour. Transonic is between subsonic and supersonic. It's that Mach zero point 0.8 to Mach 1.2 number discussed before. Please don't go there. Please don't peek around there. Please avoid that speed. Um, Past couple of years we had this tangent ogive shape, which you can see here actually. There's a mathematical way to derive it in this mini rocket I made. Um, the big picture point is that the shape is that shape for a reason. So let's not have a flight that's not within the threshold we designed the nose cone for, please. Fins, I mentioned this before. You want to drag the CP back and have the center of gravity higher, CP center of pressure. Um, Open Rocket does help optimize the fin shape as well. More fin analysis that's done is called fin flutter. Ideally, you don't have this much flutter. There's a certain threshold that the speed the fins vibrate has to be within. There is analysis that they conduct to ensure that it is within that threshold. There is this balancing act with fin design as well, I'll mention. If you make smaller fins, you have a more upward center of pressure. If you make bigger fins, you're gonna have to justify the strength of them better. Um, all in all, if you can stand on them, like you Ottawa did here, you're good to go. Other analysis includes the tube bending. Basically, when you have a center, the rocket's going to have a center of pressure here and a center of pressure here to an extent. As it goes up, it's going to bend a little bit like this. You can analyze it. It's pretty negligibly small. However, you still should acknowledge it, especially if your rocket's super long and there's not a lot of support pieces throughout it. We can also do a lot of the analysis OpenRocket suggests or does for us in-house. It is more time, but if we have a number that agrees with OpenRocket, we get more confidence in our design. There is also computational fluid dynamics, CFD. If you've ever seen the wind acting on a cow simulation or something like that, the streamlines on a car, those simulations, that CFD, it would tell us a lot of inaccuracies or other issues regarding the flow of wind throughout the rocket. Great time. I want to break it. I can keep going if you all want to, but yeah, yeah. All right. Any questions? I either explained it really good or really bad. I hope. All right, I'll go back and do it. All right, I'll get to it then. Recovery. As we discussed before, SpaceX does a lot of propulsive landing launches. We're not allowed to. That's a bummer. The solution is we separate the rocket somehow, segment it out, and we land with the parachute system of some sort. Separation, sorry, I should have mentioned this here. We typically segment recovery tasks into two categories, separations and parachutes. Separations is in charge of separating the rocket to deploy the parachutes. There are some. Go ahead.
Mentions to like military oriented rockets. Means that
Sorry,
do you make like military oriented rockets like
like bombs.
not bombs like rockets more military based like silent jets
Kind of.
and
Military is oddly involved. Not involved in what we do, but
yeah
all the stuff we work with ends up being a military component for is otherwise going to the military sometimes.
mm,
A lot of the stuff we work with otherwise goes to the military sometimes.
yeah
Okay, I guess back to this. Here's something we don't use. It's called tender descender. The idea is that it allows the rocket to separate at one point by, in this case, the nose cone popping off. Then one parachute pops up here, and then something is in here holding the main parachute. Forget fully how this mechanism works, but the idea is one separation point and one thing that holds the other chute in while the first chute is out. The pros is the one separation point is a big deal because it means we have to don't have to design the rest of the rocket as robust. We just shove all the recovery stuff at the top. Call it a day. The con is that there's a lot of risk factors. You see most teams that use them use end up either having no drogue deploy or main deploy at apogee, the top of the flight, or something in between. We could argue that three of our flights failed because of the use of tendon extenders. Reef shoots, this is something that is way beyond our pay grade, but a lot of teams do use them. The overall idea is that similar to the other one, it is one separation point. However, this parachute functions as both the drogue and the main. It has some mechanism that holds the parachute small. I've seen the reef be in the middle as well to have it kind of really thin. And then you unleash the reefing mechanism, and then a bigger chute pops out of it. So it's really cool. However, it is also incredibly hard to implement. This is what we use. It's called dual separation. The idea is we have the drogue come out and the main come out in separate locations. Um, Very notably, we don't have any risk of any ropes or wires tangling from one chute tangling another. However, we have the need to design our rocket a little more strategically because there's going to be a point where we have to push this part of the rocket way over here, and there's going to be a point where we're going to have to push this part of the rocket way over here. So we're going to have to think a little bit more about, I guess, tugging happening on all of the components. This is in very simple terms how this mechanism works. Firstly, there are these bolts called shear pins. The idea of these shear pins is that they are made of a very breakable material. Yes, this means that the only thing holding our rocket together on ascent are these three plastic screws. The idea, I have a whole demo. You put the shear pins. Also, for context, shearing is a failure mechanism that is caused by bolts breaking radially. So you put these shear pins in. It's not fitting here. Then you implement some level of explosive into there. Uh, the first of these explosives is black powder. Black powder is cheap. It is easy. However, the parachutes need to think about flames. Black powder is gunpowder, basically. Um, Apparently, it's less reliable at higher altitudes. However, it's going to depend on person on who you ask whether or not that's actually a true fact. The other potential energetic for separating the rocket is CO2. It's more expensive and it is historically for us more finicky. However, supposedly it is better at high altitudes. Then, if you want to separate the parachute, you literally break the shear pins. And so plastic bits go everywhere at 10,000 feet in the air. Hobby rocketry. Um, you want to do some level of analysis to justify that the amount of black powder and CO2 you use are sufficient. Um, Even after the analysis, you're going to want to test it. There's plenty of clips on our Discord of explosives and the rocket we're planning on launching a week from it go everywhere. This one we use way too much black powder by accident, as you can see by the fact that it is not touching the ground and has moved a solid 5 or 6 feet. The overall issue with separation that you're going to hear a lot is there's this massive area where your design is applicable. Um, you want your shear pins to comfortably survive flight. So let's say we've designed the shear pin system accordingly. Then you're going to have the issue where you want your black powder to comfortably break the shear pins, but not cause your rocket to explode into pieces. Depending on who you ask, they would put where the amount of black powder they'd want in the rocket in a different spot on this screen line. Some might say you really don't want to rupture your rocket. Some are going to say you really want to be confident that those shear pins break. I don't think either of these are wrong takes to have, nor are either of them right. The only thing that's wrong is if you break the rocket or break the shear pins, or don't break the shear pins, because that's when the problems happen. Quick overview of the parachutes. I talked about drogue and main. Maybe I should have brought the parachute system up first. Anyways, the first parachute is called the drogue parachute. The purpose of the drogue parachute is to bring the overall rocket to a terminal velocity that is not Mach 0.8, because the main parachute brings the rocket to safety, and the main parachute doesn't typically deploy until around 1,500 feet. Why not deploy the main at the top? I believe the reason is that the wind will take it very, very far, and you'll be lucky to find it. You'll have to travel very far to find it, if you can even hold a GPS signal that far. Um, both of these have very valuable purposes. Both of these have their own interesting function. We currently design our own parachutes. SRAD is doing research and developed. Parameters that matter is when we deploy the parachute, what the speed at each deployment is, size, shape, material, and this magical coefficient called the drag coefficient. If you want to find the force that is emitted anywhere, these are all findable values: area, velocity, density. However, this is kind of this magical, I made it up in a dream value. If you search up the coefficient of drag of any Tesla model, it'll spit a number out at you. But the reason they got that value is through experimentation and not analysis. And so when we talk about the analysis for parachutes, everything goes through the drag coefficient. So we have this interesting issue of, okay, yeah. So firstly, I was getting too ahead of myself. First thing, when you analyze a drogue, the drogue parachute, you want to think terminal velocity. The drag here At least considering the fact that the drogue is a third of the size of the main, and that the velocity at the top functionally is pretty well zero. You're gonna worry more about how what velocity is it going to bring the rocket down to when it's around here in the main deploys. You don't want to make it super quick because when you deploy them in, there's a lot of drag force that happens if it goes super quick. For the main parachute, there are three things that matter. First, when are you going to deploy it? You can't deploy your main above 1,500 feet, so we deploy our main at 1,500 feet because we want the maximum time uh, for potential errors to get adjusted for. Um, this is where we care about this drag force I mentioned before. We technically, as we start the design, don't know the drag coefficient, but we have to determine all of these rocket parameters based on this drag coefficient that we don't know. And that would also tell us what the final rocket velocity is. So there is this chicken before the egg design. Um, goes in the next slide actually. We do know roughly what it'll be based off history, 1.25 to 1.5, give or take. But we once again don't actually know until we test it out. So what we do is we do a drag test. Uh, some teams grab a helicopter, they grab a hot air balloon, and they drop it, and they find the terminal velocity of that. Pretty expensive. Car test. A lot of teams pull their parachutes from a car and use some level of strain gauge, and then you can reverse engineer or reverse calculate the drag coefficient. Anything you have that can give you a force based off of speed or a terminal velocity based off of height is used for drag testing. Other things that matter when we talk about parachute design, how exactly you're constructing it. There are these things called gores. These are the triangles that make the parachute. How big are they? You need to fit the parachute into the bay, into a certain segment of the rocket, this big, for example. How are you going to make it? The main parachute last year was 3 meters in diameter. It's huge. It could be a table cover, as well as we discussed before, there's black powder that goes into separation. That's flammable. How are we going to induce proper flame resistance? Another thing that should be noted is for parachute design is how are we going to connect it to the rocket? We call this tethering. You want to have a tethering design that orients the rocket so they're not doing this, so they're not clashing together. But you also want a tethering design that can hold the forces of the drag throughout the launch. You'll hear Kevlar and nylon being used as a tethering material. This is a sample of Kevlar tethering. It is tied into a knot called a chain sennit knot. The idea is if you pull on the knot, it absorbs an initial load to untie, so it kind of helps absorb energy a little better than other knots do, as well as it really helps compact everything. The other thing to note is you want to fold your parachute very methodically. You're nowhere near the parachute when it is being deployed. And you want to make sure that if you pull on it, it spans out. Because if you fail as recovery, then the rocket does not survive. So you'll see hear the words chain center knot and Z-fold at top level discussion. Um, the Z-fold is literally if you grab a piece of paper or a plastic bag, for example, you fold it, you fold it. The idea is if I pull here, it fans out and it's not going to have a personality of its own. That's how we ensure that the parachute comes out cleanly. Regarding linkages, there are two links that you'll hear talked about with recovery a lot too. First is a quick link. This is a quick link. It just connects components together. There's nothing fancy to it. We just need tethering to connect places and other places. The other link very commonly seen is called the swivel link. The idea is it can spin about itself. Every link other than the link that the parachute directly connects to is a quick link. We want to minimize spinning, so only the parachute can really spin about that point. That helps for if the rocket spins, then there's that counter spin from the swivel link. When we connect the parachutes to the rocket, there's two kinds of bolts you see. Eye bolt is this kind of thing. It is smaller, more compact. So if you have a very complex rocket design and you want to take the risk of potentially an unthreading from various components spinning, vibrations, etc., eye bolt is the solution. We successfully use only eye bolts on Winnie 4.5 or 5.0, sorry. The other kind of bolt is a U-bolt. The con is that it's bigger and bulkier, but it doesn't have that risk of unthreading. Regardless, we're talking about a load, projected drag load of around 1,000 pounds, 4,200 newtons. So everything I listed here has to be incredibly strong. Separation test, as we discussed before, now that we know what the parachute is going to look like, what's inside of it, that's another thing we're going to look at when we separation test. We want to make sure that um, not only is our analysis regarding separation, punching the rocket apart right, we want to make sure it's not going to make the chutes go on fire, as well as the chutes change how the bay interfaces, how the bay size works, etc. Quick overview for I had a lot of small pictures. Separation happens around here. There's the drill. There's the main plans. Avionics. Um, First thing, I didn't realize this till like third year. Anyone know what avionics stands for? Aviation electronics. That's why anything that flies gets called avionics, and why nothing else has that nonsense term. Avionics is just that. Electronics, avionics. Why? I don't know. Quick overview of what avionics does. The recovery moments we talked about before, all of these have an avionics aspect to it as well. Data acquisition, we want to know how fast the rocket goes. We want to have the whole story of the rocket, as well as they do some things with the camera system and the GPS, as discussed before. We want to find the thing after we launch it. Could end up in dense forest. Um, yeah. Currently, we have two commercial off-the-shelf computers. There are a bunch of other viable computers, but these are the two we use. We have to have two, one to back up the other. Right now, we use the AIM Extra and the Blue Raven. The AIM Extra distributor is a guy from Minnesota that a couple members have on speed dial, which is one to think about. Um, the reason why we currently have two different ones is because yes, the potential failure modes do double, but there's no failure mode A happens that causes nothing to deploy. We're not going to see that twice. That was kind of the thought process behind it. Quick overview of some of the sensors. Yeah, okay. First, the altimeter. We measure the height of our flight with barometers and math. You might or might not know this, but the density of the air changes as you go up, and it uses that as a reverse calculation to tell how high it is going. To accommodate for that, we need holes of certain sizes based off of how fast we go. there's a spreadsheet that the poor avionics integration guy has to plug, and it's something we typically forget to do until the very end. We have accelerometers as well, gyroscope, as well as measures XYZ acceleration. I think I ramble about this more, but this is what goes on behind the scenes when we deploy the drone chute. Um, velocity, once again, the velocity gives us a very good picture of our flight. Um, the story of last flight was we thought we were going to go Mach 0.95 and we went Mach 1.15, so we accidentally broke the sound barrier. Go us! There is also a TAM sensor. It's always been a red herring. It's always gotten in my way of analyzing the data that matters. Yeah, here we go. I rambled about it. So when we talk about this separation moment that happens at the top, as you can see from my crap flight projection, at here, it's really a tilt that happens, right? When it hits apogee, it starts to tilt, and it's that tilt plus some other sensors just to make sure it's not detecting the tilt here that causes the roll parachute to separate. Then, as we keep going down, it's this altimeter that we talked about before that causes the main to separate. Um, so recovery and avionics have to have these conversations to make sure that one, avionics knows where the recovery items are, as well as what altitudes we want all these events to happen. The other thing I'll mention is that the secondary computers, they basically ask the question, okay, we tilted. Is it deployed yet? Is it deployed yet? And if it's not deployed, they'll spit it out as well. That's a 1 to 2 second after that happens. So then if there is a burst, then there's not an immediate other burst. There's not two bursts. There's just one burst and then another. But that is how the secondary system works. GPS system, AIM-Extra has one embedded. It's called the Featherweight. Um, there's nothing fancy about it. There's a dedicated software. You don't need any Wi-Fi or anything to access them, which is kind of neat. Um, yeah, this is a handheld device. This is the module that's there. That's how we find the rocket. A lot of the airframe, sorry, yeah. Carbon fiber, you'll see, is the primary thing we use for airframe. This was also another issue I had when making this presentation. I need one thing to explain the other thing to explain the one thing. But anyways, carbon fiber has an issue where this thing called RF, radio frequency, can't go through it. But we love carbon fiber on airframe. And so there's this back and forth issue where if we have carbon fiber, we can't use the avionics system, GPS. So right now, the way we have that combated is we have no carbon fiber in the nose cone at the moment, but ideally we want the ability to make the entire rocket out of carbon fiber because it is the strongest material out there. The solution we're currently working on, that is the copper strip around Winnie 5.0 that you can see, is our own antenna that wraps around the rocket. It took a lot of analysis and a lot of back and forth design to make happen, but it did have some success and has some room for improvement. But that's that copper strip. It's actually an antenna. I discussed this before. There's some kind of arming system needed. The handful of options are key switches, finger tech, which is basically a glorified screw switch, and a screw switch. This is what a screw switch is. The idea is you can pop open a small segment of the rocket, or you can have this mounted on the side of the rocket. As the screw connects inward, it completes the circuit. We did use key switches before as well. It is literally what it sounds like. It is a car key that goes in. We didn't like them because they oftentimes either electrically or less fun mechanically failed on us. The big caveat with screw switches is you'll hear this talked about. I believe we had a system to fix this in last year's rocket, but if you unscrew it all the way out and your rocket's on the launch pad, then the screw might just fall out, which is also not fun. The other thing, whatever system screws in the screw switch will have a beeping noise. You'll hear that in ConOps. The ConOps will explain in the checklist. What is the beep noise supposed to sound like? How do we know it's actually on? All right, airframe time. Let's put everything together. The one reason Gavin's here. Airframe is the house, the skeleton, the thing you take your cute little selfie with. Um, their main job is to keep everyone happy, implement everything, and make sure the system doesn't break in on itself. First, I'll talk about the structure. You'll hear a lot of teams use carbon fiber, fiberglass, or other. Fiberglass has the RF transparency benefit, and it's kind of the Goldilocks zone in price, where it's not the crappiest stuff, but it's not the most expensive stuff. The strength normally, unless you're going crazy speeds, is sufficient. But it's not the strongest material out there. Yes, this is the same fiberglass that goes in your insulation. It's just not gonna poke you unless you're an idiot with a sander. Carbon fiber. Our bread and butter. I'll ramble about this later. It is the most expensive if you buy it off the shelf. It's not RF transparent. However, it is noticeably the strongest. I believe the ratio I've heard is if you're making your own tubes, 3 layers of fiberglass is equal to 1 layer of carbon fiber, give or take. You'll hear other materials used for the tubing material. Aluminum, when you have hybrid propulsion, they typically make that segment out of aluminum, the oxidizer section. I've heard Kevlar be used before. I've heard bad things about Kevlar, but these aren't the only two materials you'll see used. Um, yeah. Our bread and butter is carbon fiber because we get it for free. Magellan gives us material that they don't want. It is called pre-preg. Carbon fiber is literally a carbon fiber cloth. This material is pre-impregnated with some binder called epoxy. You lay it up around an aluminum tube. The idea is the aluminum tube heats up, expands quicker than the carbon fiber. The tubing cures into this tube shape. We use two kinds of tube. That's a mouthful. There's structural tubing, main, and coupler. That's the best way we word it. The coupler tubing is kind of demonstrated here. It's smaller than the tubing diametrically, should be roughly the same thickness, but the idea is it is kind of, I guess, a strut type of a material. It's how we bind the two tubings together. It needs to be in this Goldilocks zone of tightness where you have to press a little bit to fit it together, but you shouldn't require all of your strength to push it together. Um, I should have brought the physical rocket. That's okay. But the coupler is how we connect two pieces of tubing together. Bulkheads. I like to use the word floors or page dividers. They're how we segment parts of the rocket from each other. Um, they is kind of an all-encompassing term because the thrust transfer bulkhead, the recovery bulkheads, and the payload bulkheads all have different requirements. But they're these circular discs that we use to segment the parts of the rocket from each other. Fiberglass, aluminum. I haven't heard of any other materials than fiberglass and aluminum being used, but that's kind of what a bulkhead is. Nose cone, we make it 3D printed historically. I rambled about the potential of heat generation before. This is kind of where this discussion's happening. The reason we 3D printed our nose cone is because we could, because we were going Mach 0.8, the heat generation was negligibly small. That if we could prove that a 3D printed nose cone was structurally sound enough, who cares how much heat was generated? Virtually zero. A lot of teams do use fiberglass or carbon fiber to make their nose cone. However, something I personally hope we develop is a fiberglass or 3D printed nose cone. Um, and as I rambled before, we had the GPS in the nose cone for that avionics compatibility. It let us get away with having the rest of the rocket be carbon fiber and not have to care about RF transparency. Um, but the other things we'll want to consider is obviously that it's strong enough. It's the thing that bears a lot of heat and load. So now we're going to talk about how the heck we're integrating everything. First, propulsion integration. I have it 3D printed too. This is a mini motor. This mini motor has the closure seal disc. It has a little bit of a lip. And so what we do with this little lip is we have a thrust transfer bulkhead that I press fit in here and I'm not taking out. The idea is we use that little lip to transfer all of the rocket's force up the entire rocket. Um, that's the main thing that's being asked about the propulsion system is how are you transferring the load? So that's how we are transferring our load. We are putting it through here and it is emitting the force up the tubes. There should be an eyebolt here. The top here is recovery. This was a really fun thing to figure out and make sure that it wasn't going to screw the rocket over. Um, but when you look at how loads are analyzed, the recovery system is going to only pull up here. So not only is this thrust transfer bulkhead here going to be the thing that bears all of the load going up, but when you look at the drogue chute forces also go to the thrust transfer bulkhead, which I'll just leave it at that. The other thing that we have to keep note of is centering the motor. We want to ensure that this 4-inch motor is held securely through the bottom section of the tube. Fins, there's two major ways you see a lot of teams make fins. I couldn't find any other ways, surprisingly. The first is winning 4.5 method, which was bolting the fins. The other is called a tip-to-tip layup. You basically have some fiberglass, etc., connect from this tip all the way here, kind of fusing that segment of the rocket. Um, the major thing that it has to bear is flight dynamics is able to convert this into a load and a point. And if we can prove that the fin system can survive that point and that load, we're good. The other thing that is a pain to note when manufacturing the fins is flight dynamics will give you a profile and you have to get as close to that profile as possible times three. We have some fun ways to make it, but it's not beautiful. Right now we have a 3D printed core with 3 layers of carbon fiber on top. There might be other ways depending on what the fin profile is going to look like. Recovery integration. First thing, obviously, you want the base size to match what Recovery wants. Recovery did their analysis, now it's on you to make it a physical thing. The other thing I'll mention is zippering. This is a really hard topic to explain, but I'll try my best. Imagine there's a string coming out of here. When you push it, Yeah, when you push it here, you're gonna see that this is gonna want to kind of do this, right? If there were a string here, that string might go straight through that tube because that's not a load that these tubes are per se designed to bear. They're way better at dealing with loads like this, not there. So that is a historic problem that we've had. It's called zippering, where the tethering goes through the tube, kind of shown here in this crappy YouTube video cover I saw. The way we address that is by having it so that there's no zippering that can happen. As you see here, it pops out this way. When it pops out this way, there's nothing for the rope to tug onto. I don't know if it works 10 out of 10, but that's how we've historically addressed that zippering concern. And it worked last flight. So avionics integration is very much a simple game of make everything fit, please. They're going to have a lot of needs to fit batteries everywhere, and wire management isn't fun either. Lastly, you're going to want to put all switches in a readily accessible position. I'll mention this. I talked about how 3D printed parts are weak. Technically speaking, these bear close to no load. The entire avionics bay weighs a pound or two. Multiply that by the force of gravity, you get 50 newtons, 10 pounds of load, give or take. So it's not a lot of load. So it can be 3D printed. And the perk of 3D printing it is that we get away with not having to figure out how to manufacture it. The printer does it for us. Payload and operations integration. Operations has this thing called ping, where it's a post-launch noise detector. I didn't ramble about it a lot in this presentation. Jane, if you're watching this, sorry I had to draw the line somewhere. Make it fit, make them happy. Payload is probably going to be stationary because of the need that IREC imposes, where they really don't like deployed payloads and they're going to be on your case. Make it fit, and I hope future airframe leads always have someone at least look at it, because when it's a couple days before launch, you realize you haven't thought about every little detail of fitting the payload. It's not a fun couple days. All right, we're gonna play a game. Here's the launch projection. We're gonna, what time is it? Oh, I'm good on time. I'm going to snippet every moment of the launch. I'm gonna have you guys guess ways you think things could go bad. We're going to assume analysis has been done, but we're going to acknowledge as much as we can that can go bad. Okay, ready? What can go bad here?
The center with the motor wheel.
I didn't think about that. That's a good one. For the people watching here, there's only three people. I don't want to be mean to Gavin. Um, Things that I thought about that aren't fun. First, uh, most commonly, we have commercial off-the-shelf items. They sometimes misfire, which just means no ignition happens. And it's really annoying because you have all this tension thinking you're, yes,
What's it using putting stuff?
electronics. If for a commercial off the shelf motor, it's just the electronics either not working or a spark not being strong enough. With commercial off the shelf system, we're just left to hope that they have the right system. They typically have two or three igniters though. So if there is a misfire, then we're probably good to go. But it's really annoying because we're like, it's about to launch and it misfire. Okay. Um, Thrust transfer not being strong enough. We do analysis, obviously. If that happens, you're gonna see the motor go straight through the rocket. Um, Something coming loose, also an ideal. What if there's a connection point that's gone and now we don't have the drill deploy? We can't really monitor that at the moment. If the rocket starts to launch and we lose telemetry immediately, that's really annoying. We're gonna have to watch the live stream footage again to try to find where it went to locate it. And then lastly, vibration causing something loose. The vibrations are less than you think. It's not car level vibration analysis, but especially if you're going supersonic, it's something you're gonna have to think about. All right, anyone have anything? Okay, yeah, that could suck. I'll give you guys a hint. This is when the forces are the highest.
Depends, what was it called when you're vibrating?
Flutter too much?
Yeah.
Yeah, good one. I didn't think about that one actually. I'm just gonna go down the list of every component on the rocket and saying at this point, if it's gonna break right here. Actually, winning 4.5, you can find it IREC day 3. Maybe I'll do it after. That is when it failed. I don't take pride in this, but winning 4.5 went into pieces everywhere, and it happened right about there. You saw it boost, and then you saw confetti. Um, but to shoot firing early, I've seen one or two launches do it. It kind of looks funny depending on when it happens, but that's going to be right. You have forces here. Now you have another mini explosion here. That might cause some crazy damage to happen. I broke it. Did I break it? No, I didn't. Oh, I broke that. That's nice. Okay. But anyways, at this point of the launch, this is when we're gonna see if it's gonna break, it's gonna break here. Apogee. There's a very obvious thing that could happen.
The zipper machine.
Good one. Even dumber.
She got one off.
Bingo.
The bolt's not breaking or line up the rocket.
Bingo.
Repair.
The other thing that really sucks that has happened a lot for a lot of teams is the main deploying here. You're not finding it, especially if you're going way more than 10,000 feet. But the thing we're more scared of is no deployment happening. Okay, drones deployed. You actually brought up all the good discussions there too. Um, Anything I talked about that's a recovery risk earlier, flames going everywhere, etc. That's gonna happen around here. It would also be really annoying if you did your math wrong and one of this happens. And then also, I was scared of this last launch. There were some rips in the tethering because we didn't think to order more tethering. And so I was like, in my head, hoping that nothing ripped beyond failure. What? Okay. Uh, I should have had an intermediate phase. Let's pretend the main is about to deploy, but hasn't deployed yet.
Ever since you guys swapped it.
Okay?
Ever since you.
Yeah,
Maybe it wasn't told to the rocket properly.
that's a good one. Turth was in here earlier. He was the guy in charge of it. So shout out Turth. But yeah, everything that was brought up in the last step, as well as the potential of main not deploying, the rocket's gonna go think we had 60 something meters per second. That's really fast to hit the ground at. As well as zippering. Losing connection to the rocket would be unideal to have right now as well too, because we don't know fully where it would land, and we'd have a big circle that to guess from. Last week,
Saving the GPS so it's
yep.
working.
The other thing I'll ramble about is uh sometimes there's an aspect of luck with the launches as well. If our rocket ends up in a bush and the bush rips the parachutes up, we can't say we're able to launch as is because our chutes are ripped up, right? So sometimes we could just be unlucky and it lands in a bush. At Launch Canada, there's also typically at least one rocket that ends up in a body of water, which there goes your electronics. Congrats on the nominal launch. There goes your electronics. Um, Lastly, you're going to want to take note that there is a chance that something doesn't fire. I rambled about something wrong earlier. Both, all four energetics in the rocket, like the two in drogue and two in main, all of that should have fired. If you're unsure if something's fired, you're going to want to like approach it with caution because there could be black powder and live wire attached to it, which is not fun. And then I haven't heard of anyone interacting with a bear or anything, but there is the risk of a bear or a moose going near your rocket, which would make recovery a really fun time. Last part? Yeah. Common tools we use. I just want to ramble about them real quick. SolidWorks is used in CAD. We use the Google Drive system that Airframe or whoever uses it will teach you it. We're able to convert our Google Drive into a cloud-based system, which makes a lot of things easy. You'll see a lot of the critiques on SolidWorks being that they're kind of good at everything, but they're not great at anything. They're good for CAD modeling. They're good for static analysis. They're good for fluid analysis, but they're not great at anything. If you look at each individual component SolidWorks brings to the table, you're gonna find someone that can do it better, but you're not gonna find someone that can do everything SolidWorks does as well. That's my take on it, at least. We use Discord a lot. I love Discord. I hate that I'm saying I love Discord because there's the bad connotations to it. But you can find old chats and segment conversations really good with what they have. I think that's all the discussion I want to have. Oh yeah, you can also find everything quick, very easy. They have a lot of good search tools, so you can search has a link and then find an old link in a chat really easily. But it is definitely a lot at once. If you just joined the UMSATS Discord, it was half the chats, half the size when I joined, and everyone's gonna add one or two chats and make it even scarier for the new guy. Last thing, I love Google Drive, partially because I've used it, but they also have more macro capabilities. Um, the finance guy managed to find a way to embed comments from a sheet and have it send you a response email based off feedback from a sheet. And there's crazy things like that that I've never heard of Word or anything being able to do. I mean, this is made in Google for a reason. I like their UI. Last part. For the new member that is watching this for the first time, here are my tips for success. First, talk. Talk, 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 talk. If you think someone's going to be a stakeholder, if you're unsure if someone's going to be involved in what you're doing, I'd still send them a message. Example, if you're avionics integration, I would send avionics lead a message the second you're committed on that task. Hey, my name is blah 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 blah. I'm gonna be the airframe avionics integration on the airframe side. Is there anything you want me to look into? Blah 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 blah. The more everyone's talking to each other, the more the less the project managers have to enforce things happen, the less it's on certain guys to be watching that things happen. If people are talking and they're doing their part, I would have loved if everyone was talking last year because I would have had to do half the work I had to do. Oftentimes when I get messages too, I just say, "Hey, good question. This guy can answer it better." The other thing is this goes for advisors too. This goes for professionals as well. If you send someone an email asking them a question and you say thank you afterwards, they're not gonna say you suck, go find someone else to do it. They're either gonna not answer your email or they're gonna answer your email well. So talking just solves so many problems. Second thing, a lot of new members, I don't blame them. I was one of these as well, but a lot of the things that I get asked, I just Google and answer it for them when they could have Googled it themselves first. You are an engineer that is proactively learning and could very quickly become someone with a unique skill set and knowledge base, even if you're in your first year. I truly do believe that. Um, the other thing I'll mention is if you don't trust your ability to do something or put in the effort to at least try it, someone else is going to have to, which is probably one of the driving reasons why a lot of teams have the running joke of 10 people do all the work. It's because we have certain people, or there's a lot of people that don't see themselves as qualified as they are. You can see myself kind of winging certain parts. I still don't know the entire rocket, and I've been on the team for 4 plus years. But the way I've learned the best is by trusting my ability to learn and just pushing things through. This here, I've circled all of these things. I circled. Someone was pretty well new to the team, not per se in their first year, but new to the team, new to the system, and they came out and they did it. Finn's design and modifications, design and implementation, both those people were the first in their roles. Recovery, I talked about Turth earlier. He went from a semi-active recovery member to the guy that everyone leaned on to make the recovery system work at competition in like 2 weeks. Avionics integration, current airframe co-lead Nolan did that all himself. Not himself, mostly himself. Payload lead, I talked about it last year, or I talked about that earlier. Last year was everyone's first year, and they almost had a working product, and I was a horrible advisor for them, admittedly. So, believe you can. Um, go for it. It's kind of similar to what I said before. Do you think this person right here, this is my U of M ID, do you think I would have seen myself being team lead before my 21st birthday? I don't think I would have. Um, if you're lucky, you have 6 years to make your mark on this team, to beef up your resume, to do really anything that back in my day in uni, blah, 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 blah. You have like 6, 7 years to pull everything off, right? Like, seize the moment when you have it. Next, don't stop learning. Um, I will say this for every one good idea, there's at least four bad ideas. For winning 5.0 being successful, there is winning 1.0 not being successful. There's winning 3.0 not being successful. There's winning 4.0 not being successful. Winning 3.0 had two attempts, they weren't successful. And winning 5.0 was finally successful, right? That's largely because every year we failed, We looked at what we wanted to improve upon, and we made those improvements. If we do not stop learning and we do not have a culture of people that are consistently willing to fail and learn their lessons from those failures, then we are not a team that is going to go far ever. Um, I hear this often. Oh man, yeah, that happened, but this year, and then it's not like a good engineering point. I get mad when I hear that. Maybe I won't strangle you. I'll just correct you. Last year, be good to one another. University sucks. Engineering sucks. A lot of people are worked up all the time. Exams, assignments. Even if you're not in engineering, or physics. I looked at the math physics have to do in their second year. I was like, what is this nonsense? Um, Rockets is also not easy. I tried to break it down in 120 something slides. It's not easy to do. And the last point I want to make is that, yeah, making rockets is cool, but all of my favorite memories are doing things together, having good laughs, going out for sushi after the award ceremony that you attended because you have to, not because you want to. Um, those are my favorite memories. As much as making the thing is fun, it was making things together with long-term friends that I definitely cherish the most. That concludes my presentation. Thanks for listening.